Is there anywhere you could go where it's so dark you couldn't see your hand in front of your face? Could we reconstruct gravitational lensed galaxies? And would it make sense to move the Gaia mission out to Pluto? All this and more in this week's Question Show. It's time for the Question Show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down, gather them up, and I will answer them here. Now, there's two things I want to tell you about. One is that I do a special patrons only question show once a month. So I just sent out the request for questions, but then I do like a very long question show and try to get through as many comprehensively of the questions asked by the patrons. So if you aren't a patron already and you want another shot at interacting with me, that's a way to do it. And then also, if you missed the live stream, and so you know that in fact, what you're watching is less than half probably of the full question show that we record live every Monday at 5 p.m. Pacific. And we will actually release the audio for all of the overtime, all the extra stuff, again, to the patrons. So if you want to get almost guaranteed chance to get your question answered, as well as get all of the additional audio to your own personal podcast feed, go ahead and join our Patreon, patreon.com/universe today. All right, let's get into this week's questions. Na656. Are there places in space where it's so dark that you couldn't see your hand in front of your face, or is there always at least some light? This was one of the most interesting questions to think about that I've seen in a while. And, my initial response is, it wouldn't take much for you to not be able to see your hand in front of your face. But then I was thinking about it, and like if you were out in space in orbit right now, obviously the sun would be shining, you would see your hand in front of your face. But if you were in the shadow of the Earth, then you would see the Milky Way, you'd see the stars. And so you could make out the shape of your hand because of all the stars that it was blocking. And pretty much anywhere you went inside the Milky Way galaxy, it would be the same thing. You would be seeing your hand because there'd be stars all around you. It's only when you go in between the voids, in between galaxies, that you wouldn't be able to see that kind of light. And you'd have to go pretty far. So, obviously here on Earth, we can see the Large Magellanic Cloud, the Small Magellanic Clouds. They look like clouds in the sky. And so if you put your hand up in front of the Large Magellanic Cloud while you're out in space, you would see your hand moving in front of it. Andromeda Galaxy is actually really big. It's about 9 times the size of the full moon in the sky. And if you're out in space and there's nothing else there, you would absolutely see the presence of Andromeda. And it's 2.5 million light years away from us. And in fact, there are even fainter galaxies that you could see if you were out in space. You could see M33, the Triangulum galaxy. And then there are other fainter galaxies that you'd be able to see as well. Out to, I would say, about 10 light years away. And then beyond that, you just wouldn't be able to see any galaxies with the unaided eye. And so you would have to be more than about 10 light years away from a galaxy to look in all directions and not be able to see your hands moving around you. But there are still stars in between the gulfs between galaxies. They're called field stars. And they're not common, but still, if you were within a few dozen light years of a star, then you would see it. So you would have to be away from star, millions of light years away from a galaxy, and then you wouldn't see anything. It would just be blackness in all directions. One of the least dense places in the observable universe that we know of is the Betazed void, which I'm sure you've heard of this. And it's one of these voids that have opened up in between galaxies as the universe is expanding. As galaxies are starting to clump together into larger and larger structures, you're getting the gaps in between them open up bigger and bigger. And the Betazed void is 330 million light years across. And there's a really interesting quote that I read that if the Milky Way formed in the middle of the void, we wouldn't see any galaxies around us. And it wouldn't be until probably the 1960s that astronomers would finally have telescopes powerful enough to detect other galaxies in the universe. And so there are absolutely places you could go in the universe where it would just look like completely pitch black around you in all directions if you were just looking with your own eyes. But there's no place you could go with a telescope that you wouldn't know that there was the larger structure of the universe. You probably noticed the Star Trek planet name that's appeared above my shoulder. This is a way for you to vote to tell us what you thought was the best question this week. And the winner last week was Mantabello UC3GY, wondering if we could ever move moons. I thought that was a great question, and it sort of made me really think about how cool it would be to have Ganymede as our moon instead of the moon, or both. That'd be awesome. So as you're watching this episode, you'll see the different planet names pop up. Just pick the name of the planet for the question that you thought was the best, and just write it into the comments down below, and then write the rest of your question if you want, and then we'll count the votes and we'll celebrate next week. The SPAS AZ. JWST and other telescopes have provided examples of gravitational lensing and the resulting smeared image of a distant object. I've heard that it is possible to reconstruct the original non-distorted image. Has anyone done this? No, and it's impossible. Some of the most powerful observations that astronomers have made has been with these gravitational lenses, where you've got this foreground object that is very massive and it is acting like a natural telescope lens to some other object that's behind it. And as the two objects line up perfectly from our perspective, the foreground object distorts the light coming from the background object and magnify it by a lot, like by a factor of 10,000. And so imagine you had James Webb and you're looking at a galaxy, and then you had a version of James Webb that was 10,000 times more powerful. That's what you get from the gravitational lens. But when you look at these gravitational lenses, they are these kind of smears of galaxy, or you get this Einstein cross, or you get four versions of the same galaxy, but they're all smeared out by the gravity. And the reason that they're smeared out is that you've got this enormous galaxy cluster, galaxy, whatever's in the way. And it is, because of its gravity, it's focusing the light from the background object. To reconstruct the image of the galaxy that is being lensed in the background, you would need to know one of two things. You would either need to know the exact gravity of the foreground object. And of course, remember, it's not just like a sphere. It is a blob of mass. You've got galaxy clustered together into various shapes and sizes and dark matter and different distributions. And it is this massive blob that's floating in between you and that distant galaxy. And so you could only recreate the shape of the galaxy if you knew exactly what the shape of the foreground object is. And we can't know that. Or if you knew exactly what was being lensed in the background, then you could try to recreate the exact shape of the lens that's causing this object to be magnified. That said, people have tried. They use machine learning. And so you can do things like look at the current object that is being lensed by the foreground galaxy, and then you can try to recreate the original image by feeding it examples of what various galaxies are supposed to look like, and then you can try to get to some kind of result. But you'll never know you're right, because you can't actually go and see what the original galaxy looks like because it's behind the gravitational lens. And so you're stuck. But there's one cool outcome of this, and that is that if we use the solar gravitational lens, in other words, if we go out to about 550 astronomical units away from the sun, we use the sun as a natural lens and then look at objects behind it like, oh, I don't know, another Earth, right? Then we would be able to reassemble the original object after it's being lensed by the gravitational mass in front, because we know the shape of the sun and we know the shape of the gravity well that the sun is producing, and it's a sphere. And so we could then use that to recreate the original object and be able to see the exoplanet with kind of perfect clarity. And so until we can go out and measure and calculate the exact mass of the gravitational lens, only then will we be able to actually recreate what the original galaxy looks like. But in many cases, astronomers kind of don't care. I mean, sure, they would love to see the shape of the galaxy, but the thing that they're most interested in most of the time is just the light coming from that galaxy, because they do spectroscopy on that image. They take the light from the galaxy, they blow it up into this giant rainbow, they look for various dark lines in this rainbow, in the chemical signature of the galaxy, and that tells them the presence of various chemicals, tells them how much star formation is going on, tells them the rate at which it is moving away from us. Like, there's so much information that comes from spectroscopy that it doesn't matter what the shape of the galaxy is in that image. Mr. Toastyman07. If the orbit of the Earth is our current best separation for parallax astrometry, how much bigger of an orbit would we need to get a meaningful jump in measurable parallax distances? So astrometry, this is the method where you look at some star when the Earth is on one side of the sun, and then you wait until the Earth is on the other side of the sun, and then you watch to see how that star has changed in position compared to the background. And the technique is called parallax. And of course, this is where I give you the old example. You put your thumb up and then just move back and forth with your eyes. Open one eye, close the other eye, and you'll see your thumb jump back and forth. And so imagine your eyes are a spacecraft on one side of the sun and then the other side of the sun, and then your thumb is the foreground star, and then watching it jump back and forth. That's telling you, you can use trigonometry to figure out how far away your thumb is from your eyes. And the spacecraft that, of course, I won't shut up about that does this is called Gaia, and it is looking at billions of stars and measuring their distances, their motions, and also helping figure out what chemicals are in them and a lot of other things. Would Gaia work better if it was farther away from Earth? And the answer is absolutely. If you could put Gaia at Jupiter, then it would be about 5 times farther away from the sun than the Earth is from the sun. And so you would be able to look out and measure the distances to stars with about 5 times the volume of space. It's 5 times better. If you went out to Pluto, it would be 35 times better. But this comes at a cost. Think about how long it takes for Jupiter to go around the sun. With Earth, you wait 6 months for the differences of being on one side or the other of the sun. But with Jupiter, it's going to take a decade to go around the sun. So you're going to have to wait years and years and years just to get one parallax measurement. If you're doing Pluto, it will be over 200 years. It would take a long time to make those measurements. But that's not the big problem. The big problem is the data transfer rate. And so Gaia is sending home an enormous amount of data, and that's only possible because it's at the L2 point. It's only 1.5 million kilometers from Earth. Think about what happened with New Horizons. When it was out at the distance of Pluto, it took 18 months to send home all of the pictures that it took of Pluto over the course of a couple of days during its flyby. The data rate was incredibly slow. And so you're always sort of trying to strike this balance between putting a spacecraft at a place where you're going to be able to get a high data bandwidth from it, and you're going to get enough changes in parallax that you're going to be able to make the kinds of measurements that you want. And I can imagine there'll be some future where we do have some astrometry missions set out at Jupiter and people are patient. And then there's people at a computing cluster at Jupiter that are making all of the calculations, and then they're doing astrometry with 5 times the precision of what they could do from Earth. Mark Caldwell, what do you think are the chances of actually mining Psyche? 0. I don't think that anybody is going to be mining Psyche for precious minerals, then bringing them back home to Earth, and then devaluing the price of gold on planet Earth. I don't think that's going to happen. And the reason is just because it's so incredibly expensive to retrieve samples from Psyche. Think about the OSIRIS-REx mission, right? It cost hundreds of millions of dollars, flew out to Bennu, retrieved 250 grams of rock, and brought that back to Earth. That is $1 billion per kilogram for rock from an asteroid. There's a quote that I've heard, and I forget who said it, but if there were bars of gold, bars of iridium sitting nicely mined on the surface of Psyche, or on the surface of Bennu, or on the surface of any asteroid in the solar system, they would not be worth picking up. It would be too expensive to fly a mission to go and grab them and bring them home. So there is no way that we're ever going to have a time when it makes more sense to extract resources from the surface of an asteroid or mine an asteroid and bring that stuff back home to Earth. What does make sense is using that stuff locally, because then it works in reverse, right? That if you're on asteroid Psyche and you're setting up your base and you need water, it's going to be incredibly expensive to bring that water from Earth. Instead, figure out a way to find that water on the surface of Psyche and use that locally. And so in many cases, sort of imagine this every object in the solar system has this sphere around it, a gradient, and that gradient is like changing prices for how expensive it would take to bring resources to that object. And that there will eventually be, and like not soon, but tens of years, hundreds of years from now, there will be these sort of prices that it's worth it. Like, okay, it's worth it to take microchips from Earth to the moon, or it's worth it to take helium-3 from the moon to Mars. And eventually we'll work out what are all the economics of all that stuff. But no, like I can't imagine a time that we will ever be able to earn a profit from bringing metal from asteroids back to Earth. Just use them in space. Schizzerman, if you had to pick a planet in our solar system which to spend your last few seconds on, which would it be? Does freezing, exploding, or getting squished sound more enticing? They're all awful. I mean, if you were on Mars, then you would asphyxiate and freeze. If you fell into Jupiter, then you would also asphyxiate, and then you would be crushed by the enormous pressure. If you got close to the sun, you'd roast. Fell into Venus, you would roast and get crushed. So they're all awful. But there was sort of like an idea that I really liked, which is that if you were just wearing a spacesuit and maybe a coat, what are some places that you could survive in the solar system? And there aren't many, but there are a few. Like, for example, you could survive in the cloud tops of Venus at about 100 kilometers altitude. The temperature and the pressure of Venus are Earth-like. And so as long as you had a way of breathing, you could stand outside on Venus in your cloud ship and you would be able to survive. Or if you were under the ice on Europa or Enceladus, there's going to be a place where the water pressure isn't that great and you could be swimming around under the water and you would be able to survive. And then I even heard if you fell into, say, Neptune or one of the ice giants, there would be this spot for a little while where the pressure of the atmosphere pushing in on you is something that you could handle on your body. And so you could survive in that for a brief amount of time. And then you would fall deeper into the planet and then you would get crushed. So they all sound awful. I like Earth. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special Patreon-only podcast feed and get the overtime segments as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Joran, Mike Arendale, John Huber, Halsey Vandenberg, No Name, Stephen Bonnet, Peter Calloway, Jacob English, Christian Vanderbrink, and Vasilij Milosevic. Join the club at patreon.com/universetoday. Manuel Pingas. How long does it take an average density nebula of gas turn into a sun-like star? And given enough matter and time, couldn't a planet become a star? So before you can get a cloud of cold hydrogen and other elements to form into a star, it needs some kind of kick. Like, the nebula is just going to sit there for millions of years without doing anything. It's only when it receives some kind of kick, some kind of turbulence, where the gravity of the particles start to pile up and it starts to begin that process of collapsing and rotating. Now you can get like a supernova explosion going off in the area. You can have, say, the cloud end up in one of the spiral arms of the galaxy, and then you've got these sort of gravity waves that are moving through it, which are different from gravitational waves, these pressure waves that are moving through that could cause the collapse. That's why you see a lot of star-forming regions in the spiral arms of galaxies. So you could wait a long time before that process happens. But once it begins, then it doesn't take long. There are examples of stars that astronomers are seeing at different ages. They call them protostars. And in many cases, they're just 100,000 years old, and you're already getting sort of the beginnings of the star starting to form and ignite. Within 1 million years, the star has become like a protostar, and often its planets have already shown up and are orbiting, and within, say, 10 million years to 100 million years, it turns into a main sequence star, and then it's going to live for however long it will, billions of years. Now, the second part of your question, could a planet become a star with enough time? If it had a continuous source of gas that was being fed into the planet. It would just continue to gather more and more material, and eventually it would be able to become a star. But the difference between like the smallest star and a large planet like, say, Jupiter is enormous. The smallest star that could be considered like a main sequence star is a red dwarf star with about 7.5% the mass of the sun. That is like the least mass, but you could still get fusion in the core of that star. And yet Jupiter is about 1/80th that mass. And so if you went and took 80 Jupiters, mashed them together, then you get the smallest possible star. And in many cases, most star systems, when the star ignites and it's starting to send out all this radiation, it's clearing out all of the material in between all of the planets. And so there's no new sources of material that could cause that planet to grow. And so the planet formation stops and you're sort of stuck with the planets that you've got. But like people always wonder, like, is Jupiter a failed star? And like, it's only a failed star if you find 79 more Jupiters and crash them together. An old hunter. I was curious if you could explain more about the news of NASA finding amino acids on an asteroid. Does this confirm life, or does it just add to the possibility for life? So amino acids are the building blocks of life. When you look at your DNA, you are made of amino acids. And we human beings are made of, I think it's like, was it 20 different kinds of amino acids? But there are actually dozens and dozens, like, I don't know the total number, but like almost 100 amino acids are known, and maybe way more than that. I'm not a biologist. But what's amazing is that astronomers are finding that more and more of the amino acids that make up all life on Earth are already present in space. They found them in nebulae, they found them on the surface of asteroids, they found them in meteorites, they found them all through the solar system. They're in the atmosphere of various places. Like, clearly, whatever forms star systems in the first place also generates a lot of these amino acids. And yet clearly this doesn't lead, this isn't life. This is the building blocks of life. This is, if you have a bucket full of Lego, it's just a bucket of Lego. It's not a Star Destroyer yet. You've got to put it all together. And so something caused life to begin the process of going through replication, and evolution, natural selection got us to where we are today. But it's nice to know that all of the building blocks are there. So when you sort of think about it, you've got the raw materials, you've got the carbon, the oxygen, nitrogen, and then you've got sort of more complicated organic molecules, things where you've got carbons and oxygens and hydrogens put together, and you've got things like methane and oxylene and propane and things like that. And then you've got the amino acids. So they're forming into even more complicated molecules. And then those are what are made into DNA, but it's the organizing them into DNA that's the tricky part. So it means that the raw materials for life were on Earth. The raw materials for life were on asteroids. Maybe asteroids delivered the raw materials for life to Earth after the Earth formed, as well as the water. And yet we still kind of don't know how you went from non-life to life. Big unsolved question. Mr. CS83, now that we figured out how to deflect an asteroid, are rogue planets now the biggest threat to life on Earth? I mean, we've figured out how to deflect an asteroid, but we haven't really begun the process of pushing all of the potentially dangerous asteroids into safer orbits. So we theoretically know how to change the orbit of one asteroid a tiny little bit, but in theory, if we knew about a dangerous asteroid that was on the right trajectory and the right time frame, we probably could push it out of the way if that's all humanity was focused on, which would make sense if this was an imminent threat. So what is the great threat from space that humanity faces? And no, I don't think a rogue planet is a really big risk. We know that the orbits of the planets in the solar system are largely unchanged for billions and billions of years. And if there was like a giant rogue planet had passed through the solar system, then the planets would be in really weird elliptical orbits, really eccentric orbits. We don't see that. Same thing with like a rogue black hole passing through the solar system. Like that would be catastrophic to the orbits of the planets. And yet everything is pretty good. Nothing's extremely out of whack. No, the thing that is the most dangerous to us is the sun. The sun, we know, puts out really bad solar flares on a regular basis. every few thousand years. It puts out a powerful enough flare that it would fry humanity's electrical grid. It would destroy the electronics of satellites in space. Scientists have looked through the tree rings historically and seen examples of solar storms that are just off the charts to anything we've ever experienced. And the more our technology, or more of our modern society depends on electricity and interconnected networks, the more vulnerable we are to a very powerful solar storm. And I can't imagine a time that we could ever stop the sun from producing a solar storm. Like, that is next level. I guess until we turn it, until we create our Dyson sphere, the sun is going to be a threat to us. So no, the sun is by far the greatest threat from space that we face. Owen Cronin, what do you think will be the first entirely space-based manufacturing industry? Well, I mentioned earlier that I really don't think that we're going to be mining asteroids and bringing this stuff back to Earth, but I definitely think that there's going to be a need to construct things in space so that we can start using that material in space. And so when you think about our future on the moon, on Mars, we're going to be trying to live off the land. And so the first manufacturing that we're going to be doing in space is going to be some way to extract the resources that we require. So if we're on the moon and we've got a research station that is near the moon's south pole, they're going to set up some kind of excavator facility where they're pulling regolith out from these permanently shadowed craters at the south pole of the moon, and they're going to crunch up this regolith and extract out the water from that. And then they're going to be distilling it, and then they're going to be using that water for propellant, to breathe, all kinds of things. So I would say there will be a water distillery on the moon, and that will be the first manufacturing that humanity does off Earth. CJ Dubs, how are the first people on Mars expected to refuel Starship on the surface? Given the infrastructure required on Earth to launch anything, it seems like we are a long way off. The plan is to launch Starship to Mars, have it land on the surface of Mars, and then everyone who wants to disembark can. And then it's going to have resources on board to extract material from the Martian atmosphere and turn that into rocket fuel for the return journey home. So I don't know if you saw the movie The Martian, but there was a couple of examples where they were in the process of creating fuel for their spaceship. In the one case, he had to extract the rocket fuel from the spacecraft and then use that to be able to make water. He had to pull the water out of that. And so it had been created by water. They took water, mixed it with other chemicals to create, in that case it was a different kind of fuel, but you could make methane. And so the plan, as long as you have water, then, and like as long as you have hydrogen that you can extract from water, then there are various chemical processes that you can do on the surface of Mars, that you can extract carbon dioxide from the atmosphere, you can mix it with water, and then you can produce methane. And then you can just start to tank up methane inside Starship to the point that it's full. And then when you're full, then you fly back home. And it might take months, a couple of years, but it doesn't really matter. And so you'll have these Starships landing, and then they will start refueling themselves on the surface of Mars. Once they're fully refueled, then people will be able to get in them and come home. And then later on, you can imagine a larger process. Now, this is the assumption that there's water that's available. And like, we know there's water ice available at the North Pole and South Pole of Mars. We're just not sure how much of it is mixed in with the regolith at other parts of the planet. And that's why it makes the most sense possibly to land at the poles, because you've got the water, which is like the most important resource for living on Mars. And it could make sense to just bring hydrogen with you from Earth. So you launch Starship, it still keeps a large tank filled with hydrogen. You land on Mars, and then you mix the hydrogen with the carbon dioxide and energy to create methane as your rocket fuel. And once that's filled up, then you can return home. So, there are a bunch of steps that need to be done. Like, all of this has been done chemically on Earth. It's just a matter of doing it on a remote robotic spacecraft on Mars, where you're not sure where you're going to get your sources of water from. So it is challenging, but definitely not impossible. Dev Gaikwad. even though the Outer Space Treaty said the ban for weapons of mass destruction, but it never stated for conventional and electronic warfare in space, so why have we not seen wars where both nations destroy satellites? It hasn't come up yet. Now, there are many nations that have launched satellites, and there are many nations that have demonstrated that they have the ability to destroy satellites. So the United States, Russia, India, and China have all tested anti-satellite weaponry launched from airplane. You can imagine, like a fighter jet launches and then launches a special kind of missile that can actually take out a satellite. And it's bad because you get an enormous amount of debris that flies up into space, that clogs the area. There was a test from Russia where they destroyed one of their satellites, and there was so much debris that was a danger to the International Space Station that they had to dodge the International Space Station to make sure that they could keep enough distance. Like, that wasn't really sort of thinking through the consequences of that test. And so now people have called upon the world's nations to never do another anti-satellite weapons test. And I hope nobody ever does, because space is like our shared property. And if anyone fills that area with a lot of debris, it'll make it a lot riskier for anyone else who wants to go to space, go to orbit, try and use that region. So right now, like, there hasn't been a large war between spacefaring nations, but I guarantee each one of those spacefaring nations is tracking the position of all of the satellites that they would consider to be an enemy. They have weaponry at their disposal that would allow them to destroy those satellites at the beginning of the war. And if there was a real war between, I don't know, the United States and some other spacefaring nation, the first thing everybody would do was destroy each other's satellites. And whoever was left with satellites would be the one who would have eyes on the battlefield, who would be able to do communications, who would be able to have GPS. All of these things are important. So I really hope that people can change the Outer Space Treaty or come up with new international treaties to make space warfare completely off limits. But it's a pipe dream. It'll never happen. So let's just hope that nobody goes to war. Mr. Miser, were you surprised by the recent finding that antimatter falls down with gravity? I'm just a journalist, not a scientist, and so, I don't really hold an opinion in things like this. I just report on what's happening. And, this was something that I was definitely watching. It was really interesting to me that we have this thing, antimatter. We know what it is. We're able to produce it in the lab. We actually use it in certain kinds of medical scans. We produce it in particle accelerators. And yet there was just this question, does antimatter fall up or down in gravity? Now, the predictions by Einstein say that antimatter needs to fall down, that it is attracted to gravity in the same way that regular matter falls down in a gravity field, in a gravity well. But wouldn't it be cool if antimatter was also anti-gravity? And in fact, there's a lot of science fiction spacecraft ideas. Warp drives depend on something experiencing negative mass. And so if you could get negative gravity, anti-gravity, that would fulfill a lot of our sci-fi dreams. And yet, reality showed that nope, antimatter falls down just like the theories predict. No warp drive for you. So you're gonna have to come up with a new idea. So I wasn't surprised. I think this is sort of the expectation, but it would have been cool if it fell up. I would have preferred that. I would have preferred that antimatter fell up than down. But, we don't get to decide. Reality just sort of tells us what the truth is. Chris Shelton, do all solar systems have an Oort cloud? We don't know, but one of the common assumptions that astronomers make is that we're not special. And so if we have an Oort cloud with a lot of objects out in the Oort cloud, then it's assumed that other solar systems would have them too. And we got a hint that other solar systems do with the discovery of object 2I Borisov. So of course, you're probably familiar with Oumuamua, that first interstellar object that moved through the solar system. And astronomers are still arguing about what it is. You know, is it an asteroid? Is it a comet? Is it like a hydrogen iceberg? Is it a solar sail from another civilization? And it's an interesting object. While Borisov, the second one that was seen, was just like was pure comet. It exhibited every single thing you would want a comet to do. It outgassed in the right way, it grew a tail in the right way, and it behaved exactly as a comet should. And yet it came from another star system, so it must have come from another solar system's Oort cloud. Now, we can't see our own Oort cloud. We can't see the Oort clouds of other star systems, so it's going to be a while before we can really tell. But time to drop the Vera Rubin comment. When the Vera Rubin telescope comes online, then it's going to be finding millions of comets and asteroids moving through the solar system, many interstellar objects. And from that, astronomers will be able to start understanding what is the chemical composition of these interstellar objects, and then compare that to the chemical composition of the comets that we see here in the solar system. And there's also, the European Space Agency is planning a comet interceptor mission, where ideally they'll wait for an interstellar object. When one is detected that's on the right trajectory, they'll send the spacecraft at it. It will do a flyby and analyze the surface pretty carefully. And then from that, astronomers will get a much better sense of what is the composition of comets coming from other solar systems. And after a while, when we've seen hundreds, thousands of these things, we'll get a much better sense of how normal our comets are compared to other star systems. Like, could you imagine if we returned a sample from another star system, like back to Earth? Like if you chased down Oumuamua or you chased down Borisov and you grabbed a sample and you brought it back home to Earth. Like, we're also excited about the idea of building an interstellar probe to go to another star system. What if we could go to Proxima Centauri? Well, the universe is throwing samples at us, and all we need to do is catch them and study them and learn about the rest of the universe. So I think personally, retrieving a sample from an interstellar object should be an enormous priority. And like, it's a moonshot. It is something that is incredibly complicated, would require an enormous amount of engineering capability and timing, and yet we would have material that was formed around another sun. And I think that would be great. All right, those were all the questions that we had this week. Thank everyone who asked your questions in the YouTube chat, and thanks to everybody who showed up live on Monday at 5 p.m. for the live show. Now, I'm going to talk about some media that I really like in a second, but first, I'd like to thank our patrons. Thanks to David Richards, Mark Anstis, Antonio Lofilar, Dustin Cable, Vlad Shiplin, George, Andrew M. Gross, Jeremy Mattern, Josh Schultz, and Jordan Young, who support us at the Master of the Universe level, and all of our other supporters on Patreon. So I mentioned last week that I was really excited about the return of For All Mankind. So the other show that I'm probably more excited about the return of is Invincible. And this is a animated show that's going to be on Prime Video. The first season, well, it's about essentially Superman and Superman's son. And the equivalent of Superman, it's Omni-Man, is teaching his son how to be a superhero. And he's a member of the equivalent of the Justice League of America, but in this alternate comic book verse. And you kind of go into it thinking, okay, this is just like some kind of lighthearted superhero romp. And then it just goes in directions you were not prepared for. Like, I think it's the best show, definitely the best animated show that I've seen in the last couple of years. And not for children, but it is so good, so surprising. It is bracing. And I'm really looking forward to season 2, which starts on November 3rd. So if you haven't already, now's your chance to catch up, watch the first season of Invincible, and then join me in just a couple of weeks when we start the second season.